Can everyone hear me? Okay.
Yeah.
Okay. Hi everyone, welcome back. And today we're going to continue our discussion of nonlinear polarization. And actually at the end of today, we're going to derive the equation that you guys are going to use throughout this semester, okay, and see how you can work with light and matter interaction in classical picture. Okay, so in last week, okay, we kind of tell you guys how to build a microscopic and macroscopic connection between light and matter interaction. The way to do it is that your polarization can be written as the macroscopic polarization can be written as the number of charge density times the charge, and then the average or expected displacement of your charge. In most cases, it's electron. And then what you can do is that you can solve this R, okay, this displacement, in the presence of an electrical field, okay, for each molecule. And for different molecule, you have different potential. You have different potential well in your molecule, and then you have different response in this way. In this way, you can get different polarization for different materials. And last week, we talked about the linear case, where the equation of motion of the charge inside a molecule is, okay, this is MA, this is the dissipative force, okay. This is the restoring force, like the spring in the harmonic oscillator, and then equal to the electrical force from the external E act on the charge Q. And then we know the solution to this is, just put it this way, in this case the solution is Q divided by M. Okay. Say E. Okay. So omega 1 is the frequency of the optical wave, and then the omega naught, okay, is the intrinsic frequency of this harmonic oscillator. Okay, one moment. Okay, it's a harmonic oscillator here. And from here, we have said that you can derive refraction index, dispersion, absorption, all kind of things, all kind of linear things. And next, what we said is, okay, this is a simple linear case, but then if you do Taylor expansion of the potential well, you can actually see high order terms. For example, this is kx, and then you can also have kx squared, okay, kx squared. This is a nonlinear term, and then in previous class, okay, you guys saw that if you have nonlinear term, then your solution cannot be written down as your displacement of your charge is no longer linearly proportional to your electrical field, right? Because when you plug this back in here, x squared, you will see that the x squared would generate 2I omega t term, right? So you actually generate a frequency doubling term, okay? And then the frequency doubling term cannot, cancel out with any other term here, so you have to write down this as a perturbation theory, and then you will see that you will generate a series frequency in X, and then therefore a series frequency in P, and eventually a series frequencies in your electrical field. Okay. Now today we will first briefly introduce, okay, the classical picture of what perturbation method looks like, And then we will actually apply this to the Maxwell equation, okay, and then get you and derive the equation that's going to help us to solve the nonlinear optics. Okay, so here because we assume that we're doing perturbation, so one thing we can assume is alpha is much smaller than 1, right? It's like the motion of the charge is very small, so the dominant potential is still the harmonic oscillator potential, and then the higher order term is a small term. Okay, and because of this, the perturbation that because this alpha term is a small term, then something we can do is that we can expand x, right? X in here is a function of time, okay? Also a function of E, K, right? And also alpha, right? If you solve position, okay? If you solve this equation, the position will be a function of all these variables. And one thing you can do is that now, because alpha is a small number, then you can actually expand x in terms of alpha, right? So the zero order is that when alpha is 0, okay, then you actually get this solution. So what you can have is a zero order solution, x1 e to the minus I omega 1t, okay? And then you have the first order be alpha x2 e to the minus I omega 2t, right? And then you can have third order and keep going. Okay, so this is a Taylor expansion. Because x is a function of alpha, and then alpha is a small number, then you can always make this Taylor expansion. Okay. And now what you can do is that, okay, because you have assumed this is a solution form, this is a standard way in perturbation theory, you can plug this equation back into here, okay, back into here. And typically when you have nonlinear term, you cannot simply plug back the complex number. You cannot simply plug back the exponential term. Usually what you need to do is that you should also include the complex conjugate altogether. And the reason is actually fairly simple. Is because imagine, okay, you have x1 plus x1 star, right? This is your real x1. Suppose this is your real x, right? You can write it down as the real part and the imaginary part. Oh, sorry, you can write it down as one component and plus its complex conjugate, right? This will always give you a real number. And if you look at x squared, right? If you do x1, if you calculate this, then you get x1 squared plus x1 conjugate squared plus 2 x1 conjugate, right? This is what you will get by squaring x. But if you just carry one component, for example, you just carry this minus omega term, okay? And then you think, okay, just like before, and then you think after the calculation, and now I add complex conjugate, that wouldn't go back to here, right? Because if you look at it, if x1 squared plus its complex conjugate, x1 squared star, so the first two terms are the same, but then you miss the third term. Okay, you miss some cross terms. And so this is, later you guys will practice this a lot, is that whenever you see a nonlinear term, you have to write down, okay, the electrical field in its complete form, okay, instead of just calculate the negative frequency term and then at the end add complex conjugate. Okay, that would not work here in nonlinear term. Okay, so here for simplicity, and this is wrong. Okay, I don't want to carry all the terms here. For simplicity, let's just ignore this first. Say ignore this first. Okay, and then let's just plug this part back in and then see, okay, what we will have in this equation. Okay, then when you plug it back, the left-hand side. Okay, the first three terms would be m d squared dx squared, sorry, dt squared plus gamma d dt, okay, plus k, right? And then x1 e to the minus I omega 1t, alpha x2 e to the minus I omega 2t, and keep going. Okay, this is the first three term. And then plus your nonlinear term, alpha is here, k, and then x1 e to the minus I omega 1t plus alpha x2 e to the minus I omega 2t, and keep going, square, okay? And this thing equals to q e, and let's say e knob e to the minus I omega 1t, okay? And then now, one thing you can do now is that you see that some of the term has alpha, some of the term don't, right? And then some of the term might have 2 alpha, right? If you actually have 3 alpha, right? If this term square it, then you have alpha square, and then there's another alpha in the front, right? And we already assume that alpha is something much, much smaller than 1. And then you can do Taylor expansion on your x, right, on your solution. Then what you can do here is also, think about it, is that suppose there's a term that doesn't have alpha, and then there's a term that has alpha, right? And the thing that you can assume now is that this part will be much, much smaller than this part, right? So if, say, this equation equals to 0, then according to perturbation theory, what you can do is say, okay, this, whatever it is in this bracket has to be 0, and then whatever in this bracket has to be 0, right? Because alpha is a very small number. There's no way that this bracket can balance this bracket, okay? So we can follow this thought, and then what we can do is collect the terms, okay, according to their order of alpha, right? And then the 0 order is a term that doesn't have any alpha in it, and that is, okay, this term and this term, right? So alpha 0 term, alpha 0 order will be m d squared dx dt squared plus, okay, x e to the minus I omega 1t equals to q e knob, okay? So this is alpha 0 order, okay? You collect all the term that doesn't contain alpha and then put them into an equation, right? Because they have to balance each other, because the other terms that contain alpha is much, much smaller than all these terms, right? Okay, and if you look at this, what is this equation? This equation is simply the case for linear harmonic oscillator, right? And then so the solution is very clear, it's here. Okay, the solution is here. And just in case you guys forget, omega 1 equal to k divided by m. Okay, this is the intrinsic frequency of harmonic oscillator. And now the next one would be, okay, I want to write down all the terms that contain alpha and only alpha, okay, 1 alpha here. Then you can see this term multiply with this, right? Okay, you have all the alpha. And then here is probably alpha k. And then in this square, okay, x squared, the only way to have no alpha is the first term, okay? You get the square of the first term, right? As long as you go to the cross term, you will always pick up alpha, okay? So for the alpha first order, then you will have is alpha, this alpha going in the front, and then m d squared dt squared gamma d dt k x2 e to the minus I omega 2t. Okay, this is here. And then another alpha term, alpha k, okay, alpha k, and then square of this okay. So these are the only terms that have alpha in it, okay, alpha to the first order in it. And they have to balance each other, okay? So this is also 0, right? So now if you look at it, this equation, okay, if you look at it, I can move it into a form that looks more familiar to this order. It's by moving the last term to the right-hand side, okay, of the equation, right? And then you see that you have alpha on the left-hand side, alpha on the right-hand side, and then they cancel each other, right? So what is left is, again, a forced harmonic oscillator, right? You have on the left-hand side, if you compare this to the first order alpha equation to zero order alpha equation, okay? On the left-hand side is harmonic oscillator, okay? And then on the right-hand side is a force, right? Periodic force. And only in this case, the periodic force is kx1 squared e to this, right? This is your harmonic force. And then now we already know what x1 is. Okay, we solve x1 from the zero order. So in this way, you can actually solve x2, right, by plugging in x1, right? So the solution is actually on page 9 in the note, and I can kind of write it down here. x2 equal to q squared m to the third. Okay, square. And this square comes from the x1 square, okay, from here. And then you have omega naught square minus 4. Okay, and then there's the E1 square e to the minus 2I omega 1t. Okay. So you see that because in the nonlinear term you pick up x1 squared, and then because x1 is a linear solution, it's proportional to the external electrical field you applied, okay, that's from the light. So then when you solve x2, okay, the second order, then what will happen is that your motion, the second order motion, is proportional to electrical field square, right? It's no longer a linear relationship, but a square relationship, okay? And because the electrical field actually have a frequency, right? This is light, so your frequency will be 2 omega 1, right? So you generate the you generate harmonic, okay, of your fundamental frequency, okay? This is sometimes called second harmonic generation, okay? And you can kind of, see how it will go from here, okay? Is that the third order would have e to the third, okay? The fourth order will have e to the fourth, okay? Just because the way that you pick up extra alpha, okay, is by doing this square thing, right? So every time you pick up an alpha, you pick up another e here, okay? You can try to work out the math. We're not going to, we're not going to be we're not going to, go through all the details, but the solution, well, the conclusion we can draw here is xn, okay, the nth order will be proportional to, in this case, very simple case, only one input, will be proportional to e to the n. Okay, proportional to e to the n. And okay, any questions here? No? Okay, good. And by the way, this is a standard classical perturbation theory. And then in quantum, there's a different version, but the idea is kind of the same. Is that you assume a solution, then you plug back, and you use the previous order to solve the next order. Okay. Okay. And this is also equivalent to a linearization of a nonlinear equation. Okay. In that case, it's also the same as that well, if you look at it, we're doing exactly the same here. Is that there's a nonlinear term, you don't know how to solve it. Once you use perturbation theory, then all the equation you derive is actually linear equation. Okay, so it's the same method, and then just in different situations, people call it different names. Okay, and we know that the x eventually, okay, that's how you connect with your polarization p, right? P. So if you put all the x back into the p, the polarization, then what you will get is that you will get the polarization has terms that's, for example, okay, linear to the usually there's epsilon here, linear to your electrical field. Okay, that's a linear term, and then okay, proportional to the electrical square term, and also e to the third, right, and keep going. Right, keep going. This is because your position solution, okay, follow this each order. Okay, you add an order, you add an order to the e. Okay. This is how you get this. And there's actually an easier, okay, or more intuitive way to make this argument, is that the argument is very, very simple, is that let me see where I can do this. Okay. The argument is very simple, is that your polarization is a function of E, right? And then you know that the nonlinear effect, you can only see it, okay, by experimental observation, you can only see it at high intensity, high light intensity, right? Imagine you just have two, for example, two flash, okay, they shine towards different areas, and then what you will see is that they just pass through each other, okay, there's no interaction, okay? So if the polarization, okay, if the polarization effect, the nonlinear effect is the nonlinear effect only shows up at large electrical field, then what you can do is that you can actually do a Taylor expansion of the polarization in terms of the electrical field. Okay, just like what you have done here, do the x in terms of alpha, right? You can do the same, the polarization in terms of the electrical field. Okay, so then you will get the first order term, okay, and then second order term, and then keep going, okay? So it's a very simple Taylor expansion. So now you can kind of see, okay, there are two ways you can derive this, and then they are kind of the same. The first is just a mathematical way, okay, arguing that this term, as long as the second order term is much, much smaller than the first order term, the third order term is smaller than the second order term, then you can always do this Taylor expansion from a mathematical point of view. Okay. The other way you can argue it is that, okay, you know where the polarization really come from, and then you know that how the charge will move inside a molecule or atom, and then you can use perturbation theory, which is again a Taylor expansion, and then you can actually get the same expression here. Okay, so the takeaway here is that for polarization, nonlinear polarization, the way that you actually calculate it is to do Taylor expansion. Okay, and then when you do Taylor expansion, there are coefficients showing up in the front, and this coefficient, okay, depends on the material. Right, as you see here, different potential well will give you different coefficient, okay? And this is typically what you would do in an actual experiment, is that you get a material, want to do certain nonlinear thing, and then you look up the table, and then you see, okay, there's a number called chi, okay, chi1, chi2, and then you can calculate what will happen, okay? Any questions on this part? Okay, good. If no, then we can take this perturbation and then, put this polarization back into the Maxwell equation and then see what that will produce. And one thing I want to mention is that the perturbation method is not always correct, right? You can imagine that if the electrical field is very strong and they violate that the next order is much, much smaller than the previous order, then the mathematical foundation of perturbation no longer holds. And you might wonder, okay, when would that happen? It actually can happen now, well, by two different ways. One is that in some national lab, for example, in Lawrence, Berkeley Lawrence National Lab, their laser power is just very, very powerful. I think it's usually, okay, the power, the laser pointer you use is milliwatt power, okay? And the eye safety level is 5 milliwatt at visible wavelength. Okay, that's about the amount of, that's the amount of laser you should see, okay, with your eye. If you go beyond that, you could be blind, okay, by this. And in typical lab, okay, for example, my lab and also in, let's say, Joe Campbell's lab and Julius Berlin's lab, we have optical amplifier that typically can go to 10 watt, okay, 10 watt. It's about the same amount of power of a light bulb, or LED light bulb, but then all the power is focused on a very small point, okay, so you can see that it can really cause a lot of damage. Most university labs usually don't go beyond this. Okay, there's a reason for that, is that when you put this amount of power into a piece of fiber, right? Optical fiber is one of the best carriers for light. It will start to damage the fiber, okay? And so if you go beyond this, usually the laser or the amplifier you get will be free space, okay, free space. And then I know that some lab that work in high power laser, usually they go into kilowatt, okay, kilowatt. Okay, so that's a lot of power, okay. The kilowatt is usually the power you get from a microwave, okay. Used to heat, a turkey, but then now you just hit a tiny point, right? You can imagine the damage. And in some extreme experiment in national labs, sometimes, if my memory is correct, the number can go to gigawatt. Okay, it's 10 to the 9th. Okay, 10 to the 9th. And the reason, okay, you might wonder, okay, why people want to do this? There's, well, I'm not really up to date in this research area, but what you can do is that if the power is really high, I don't know how much you guys know about nuclear fusion. Is that the nuclear fusion is probably the cleanest, the best way to generate clean energy. And the reason that you need it, well, but the condition, okay, to put two, for example, neutron and proton and put all this together, okay, you need these elements to be in a high pressure, high temperature environment, well confined. And then using laser is one of the possible way, okay, one of the possible way to do this. But if you actually visit Lawrence lab, you see how giant that laser is. You would think, okay, maybe that's not the right way to do it, because to power this up, you need a lot of power, and then the net gain, okay, from a fusion power a fusion power generator, the power generator would not compensate the laser you use. Okay, and then also people are thinking, okay. Using a laser as weapon. Personally, I don't think that's a good idea. Is because laser actually water absorb laser easily, right? So if it rains or if there's a little bit of fog, then your powerful, expensive weapon is no longer useful. The only way that could work is in space, right? That's why there's a Star Wars thing back in the 1980s. And I think that has been proven to be too expensive to be true, right? You can, it's true that in free space, well, it's true that in space, a laser can travel without friction, right? It's just without absorption, but so is bullet, right? Bullet can travel in space without any friction, right? So I don't see a point of building a powerful laser and then to damage other satellite while you can simply have a bullet and then damage the satellite. Okay, so but these are the powerful lasers, and then when they shine on materials, what will happen is that it would actually shock your electron, and then it become a free electron actually. Okay, it will kick it out from the potential well, and then you will see crazy harmonics. Okay, and then in a lot of universities, people start to use this method. Well, not only powerful laser, but then since the electron will be kicked out of the potential well, so actually people start to think about, okay, can we start with a plasma? Okay, start with something that the electron is free from the beginning, and then people can generate really crazy harmonics. They can. I think the record now is somewhere around 30th harmonics. Okay, so if your input is omega, the output is 30 omega. Okay, 30 omega. So if you put a visible light, and then what you generate could be X-ray, right? So it's kind of very amazing. And then there are a lot of excellent work. I think one of the center for this study is at UCLA. I know some other universities also are doing very well in this area. Okay. Okay, now let's go to plug in the nonlinear polarization back into the Maxwell equation. And then before that, I want to kind of re-emphasize what we are looking for in this calculation. What we're looking for is suppose you have a waveguide or you have a piece of media, right? And then you have light inputting from one side, and then light output from the other side. Okay? And the question you try to answer is that suppose I input E in, or E, Z equals 0. Okay, this is Z. Okay, what would be the output? Okay, in the presence of nonlinear polarization, right? If you input something, what would be the output? A very simple question. And then our equation should be formulated in a way that we can answer this easily, right? Answer this easily. Okay. So the way we do this is that, one second, is that we go back to the Maxwell equation and then we see, okay, what we can get from there. So we all know that, okay, I won't repeat here. For the Maxwell equation without free charge, without free current, you will have all this. Okay, exactly the same as before. And then the only difference is that previously we have D as in linear case, right? We have D proportional to electrical field, and then you have epsilon r here. Okay, here what we have is D equal to epsilon E plus polarization, right? And then the polarization can be and the polarization is the Taylor expansion of the electrical field. Later we'll actually write down this equation in a much better way because if you think about it, there's a problem with this expression is that displacement field is a field, right? It's a vector. Okay, the first order is fine. It's because this is a vector. But then the second order it has a problem, right? It's E squared, right? If it's a vector, and then if you write down a vector and then it's a square, and it gives you a number. Okay, a vector cannot equal to a number. So later we'll fix this by using tensor. Okay. So just want you guys to be aware of this issue. Okay. So we can do exactly the same thing, okay, as previously, and then how we get the the wave equation for light. We can do exactly the same thing, but this time keep in mind that we have polarization here. Okay, polarization here. Okay, so the way that you can do, calculate EM field is that you do a curl, okay, of this equation and then plug this back in here. And then I will actually skip all the steps and just give you the answer on the left-hand side when you do double curl of E, okay, equal to this, and then you plug this back in there, equals to minus mu right, and then we call this left-hand side, right-hand side, right? And then this side, we know that, okay, this equal to minus in the assumption that we're solving plane wave, okay, in the assumption we're solving plane wave, okay? And then further in the plane wave assumption, okay, if we go down z direction and then the electrical field is pointing at x direction, then the same as before, this part we can get to as simple as this, right? As simple as this. Okay. Now a critical difference now about the E is that previously we write down E as E right, this is how we write it down previously. There's an amplitude, there's oscillation in time, oscillation in space, right? But this equation cannot work here is because now with nonlinear polarization, okay, you know that there will be new frequency being generated, and also you know that when it generates, it doesn't generate all at once, right? So it has to slowly increase. So that means your amplitude would depend on the z, okay, depend on the propagation position. Okay, so for example, at first the fundamental, the input wave will have maximum amplitude, and then as it gives energy to harmonic oscillation, it will lose some of the amplitude, right? So your amplitude for the fundamental frequency should drop, okay, with z, right? So very simply, one thing you can do here is that, okay, you add a z here. Okay, you add z here, and then of course complex conjugate. And the other thing is that there are multiple frequency components. So you add j, right? Different components. Well, there are different frequency components, and then because it's wave, so you can do a linear superposition of them. Okay. And if you look at this equation now, okay, on the left-hand side, on the left-hand side, it's linear. Okay, it's linear, so that you can calculate one of these components, and then assume it's the same for all other components. Right? You can assume the same because j is only an index. Right? It's only an index. It doesn't carry any real information here. The only time that you should be careful is when you calculate nonlinear terms. Right? When you calculate nonlinear terms, then all these different terms will product with each other. Okay, that's where you need to start to consider different components. Okay, so let's say if we take only the first components and we calculate this, and let's see, we can make this look a little bit nicer. Okay, because there are two minus signs here, and then the d can be decomposed into a term that we really like. Right, the term that we previously already calculated, and then the p term here, right? So let's see here, E, D, we can do this, Okay, we can do this. Another way that we sometimes do, but then it depends on what you are trying to calculate. Okay, the other way that you can write this down is that if you look at it, the linear term here. Okay, after the calculation, this term will become refraction index. Right, because it's linear, it will become refraction index. And if in this term there's no absorption, let's say if there's no absorption, then this term would just become the real part of refraction index, and then your solution, okay, will be the same as what we learned last week, right? You would have a speed of light divided by the refraction index, okay, and then you will have no dependent of E if you just include this term. E will not depend on Z if you just include this term, okay? And then if you have absorption, then you can imagine, okay, then of course this will have exponential decrease, okay, as it propagates, okay? And usually in this class, we don't care about absorption, okay? It's just we assume we live in a very simple world, and then no absorption. And in that case, there's no reason to carry this around, okay? There's no reason to carry this around, but something you can do is you do this. You put the linear term back, okay, into here, and then you only have nonlinear term here. Okay, nonlinear terms. And when you do research, okay, when you calculate real stuff, be very careful, okay, when you try to make any type of simplification, because there's a number of exceptions when you try to do this. For example, if you're doing with crystal structure and then it has a double refraction effect, okay, then you kind of cannot write it down in this way. Okay, there's a lot of exceptions, but in this class, I mean, we don't really worry about those. I want to give you guys a simplest mathematical form that you can grab the physics here. Okay, so then what we can do here is that, okay, you can plug the D back in here, and then this term very well. We have calculated before, and then the only new term here is a nonlinear polarization term, and then the other thing new is that you have a position dependence of your electrical field. Okay, so if you plug that back in and then move the term, okay, this to this side, and then there's a minus sign here, so you can cancel them out. Then what you will have is you have, okay, this one, and then minus mu. Okay, this is this linear term here. Plug in back here, move to the left, and then equal to equal to this. Okay, so if you look at this, this is already a second order differential equations, okay, and then differential is on T and on Z, and in principle you can solve it. Okay, in principle you can solve it, and of course we're lazier than that. Okay, so second order equation is not good enough for us. We want first order equation. Okay, so what we do is that we again make assumptions, and then we make assumptions to make this even easier for us, even more easier for us. So one exception, well, one way you can kind of think of it is that suppose a nonlinear polarization term is 0, right? Is 0. Then there should be terms on the left-hand side that give you back the light wave equation that give you the speed of light, right? So there's some equation you can use on the left-hand side. So probably when you start to calculate the left-hand side, there will be a few terms that they cancel out each other. Okay, they will be cancel out each other. The guess would be any term that does not involve with spatial dependence of E on Z, okay, those terms, they should be able to cancel each other because those terms are there even when you have nonlinear polarization equal to 0. Okay, that is the guess you can make. Okay, then what we can do here is that on the left-hand side, just to to make life a little bit simpler, we calculate the left-hand side is linear, right? If you look at it, the left-hand side is linear. So you only calculate one frequency components, and then you apply it to all of them. Okay, so let's do that. Let's see which one I use. Okay. I think I use a very let's say E1. Okay. Let's just write down as E. Okay. E, and then let's see. The first term, partial square, partial Z square. And then on E to the minus I omega t plus I k z, right? And then you see that this operation is on Z, so the time-dependent term actually doesn't matter, right? Doesn't matter. So you erase this, and then later, after you finish this calculation, you add the time-dependent term back, right? So you first calculate this. Or if you want, you write it in the front. Okay. So when you calculate this term, what you can see here is that this differential, okay, it will act on the exponential term. It will also act on the E term, right? So there are two terms here. And so what you will get is that you have, do it for the first time. Do the first derivative. Right? You act on E, that's very simple. You get partial E, partial Z, right? And then if you operate on the second term, the chain rule, right, you get IK. Right, act on the exponential term, you get this. Okay. And then you do this differential again, and then what you will see is that this act on IK, get an IK. This act on this, you get a second order differential, right? And then this act on EZ, then you get differential. On this act on IK, you get another IK here, right? So what you will get eventually will be IK partial Z e to the IKZ, okay, and then e to the IKZ. Okay, and then this act on this is again the same term, so you have a 2 in the front, and then you have this act on exponential term, IK come out, so you have a minus sign here. Okay, minus k squared EZ e to the IKZ, right? E to the IKZ. So this is what you get with this term, and then now if you want, you can add back the minus I omega t term, right? Okay, so you get this term. And then you see here there's second order differential, first order differential, no differential. And then of course later you can imagine, okay, we want to get rid of this. Okay, and then if you're really creative, you want to get rid of this, and then there's no equation to calculate, right? Okay, and the next thing is we add back this term. Okay, add back this term. Again, it's linear. So linear, you take one frequency components, and then differential on time would be, twice differential on time will be I omega square, right? I omega square come in the front, and I will become minus 1. So there's minus minus, they cancel each other. This will be this omega square mu naught epsilon r, and then this is E z okay, e to the minus I omega t plus ikz. Okay, this is the left-hand side. Left-hand side of the equation look like this. Okay, and then the first thing we're going to do here is that you can show that these two terms equal to each other. Okay, equal to each other. So previously in the wave equation, what we get is that the k is a wave vector, right, equal to 2 pi n divided by lambda. And then if you do some calculation, it will also equal to n omega divided by c, right, n omega divided by c. And then we know that n is just epsilon r square root of epsilon r. Okay, and it's this. And then omega is just omega, and c, see here. C is 1 over square root of mu naught epsilon naught. I think this is correct. Okay. Yeah, I don't have that on my notes, so if it's wrong, just let me know. Okay. And now you see here there's a k square term. Okay, so if you square all this, so k square, and then it will be equal to epsilon. Well, mu naught epsilon naught will go on the top, so it will be mu naught epsilon naught because it's square, right? So your square root goes away, and epsilon r, okay? And then there's omega square, right? This is what your k is, okay? This is what your k is in plane wave, okay? In plane wave. So every time you cancel something, you have to be very sure about what the assumption is, okay? So here the assumption is plane wave, okay? If it's not plane wave, you have to double check, right? So if you look at these two terms here, okay, ez exponential omega term, k term, omega term, k term, and then this coefficient in the front, okay, they cancel each other, right? So this term, okay, goes away, okay? And they actually make a lot of sense, right? This is exactly what we, before we do the calculation, we speculate this, is any term that's not depend on z, okay, should go away because this will simply give you the equation, the wave propagation equation in free space. Okay, this is okay. So the left-hand side, okay, reduced to 2ik partial e partial z e to the plus second order derivative ez. Okay, and then you have exponential. Okay, any questions so far? Okay, if no, then we're going to, let's see, we can remove this. If no, then we can start to make an argument, okay, make an argument how we can get rid of the square term here, okay, how we can get rid of this. Okay, so now let's think about what this wave really looks like, okay, what this wave really look like. So EZ describe what E, depending on Z, actually describe your wave envelope, right? So this is Z direction. z direction, okay? Suppose your wave is first increase and then decrease. This is what your wave envelope will look like. And the oscillation term here inside is a phase term, okay? So what it will look like is like this. All right, it's oscillating inside. Okay, we have seen this when we discuss phase velocity, group velocity, right? So this is the phase here, okay, and this is the envelope. Okay, now if you look at this, which one changed faster? Of course, the phase term, right? The phase term changed faster, and then how fast it changed? Well, it switched 2 pi every wavelength, right? This is how it changed. So k, as you can see, their definition 2 pi divided by lambda, right? So the phase changed 2 pi every lambda, right? This is how fast it changed. And the envelope usually changed much slower, unless your nonlinear effect is really strong, that you can kick up the power, within one wavelength, okay? And that's an extreme situation that you don't have to worry about in most situations. Okay, so then you can see is that this term partial e partial z, okay, should be much smaller than right the same e, but then your differential is on the phase term. Right, because this can give you 2 pi change over one wavelength, and this gives you a change at a much slower pace. Right. So if you look at it, what this really means is that when you have second order derivative here, okay, you're looking at a much slower change than this k term times the first order derivative. Okay. This only derivative once, and then it multiplies k, which is a large number, right? Because this is IKE. Right? Okay, this is exactly what we do here. Is that okay? For the first order derivative, instead of taking another derivative, what you do is take a derivative of the IK term. Okay, and this term will be much larger than making another derivative. Okay, so or the other way you can write it down is like this. Okay, you can write it down as this. Okay, so much larger, and then what you can do is okay, since it's a very small term, you neglect it. Okay, and there's a name for this. It's called slow varying amplitude approximation. What it says is that the amplitude change of your wave, of your light, is much slower than the phase change, okay, in your envelope. Okay, slow varying envelope approximation. Once you do that, then the left-hand side is extremely simple now. You only have one term left. Okay, you only have one term left, and this is exactly what we want. Okay, so put it down here. So now the left-hand side, one term. Okay, right-hand side is this. But then remember, okay, you need to add back all the frequency components now. Okay, so the left-hand side will equal to the sum of all frequency components, and then 2ik. Okay, partial z. Complex conjugate. Okay, this is the left-hand side. And then the right-hand side, well, there's not much you can do about the right-hand side, just one term. Okay, the right-hand side is mu naught square partial t square p nonlinear polarization. okay, nonlinear polarization. So this is the equation, the nonlinear equation that you guys are going to use, okay, a lot in this class. And regarding the left-hand side, regarding the right-hand side, we briefly said that what you need to do, okay, is to do a Taylor expansion of the nonlinear polarization in terms of the electrical field, right? In terms of electrical field. So what you have, the electrical field is this one, okay? What you have is a nonlinear polarization. Okay, nonlinear polarization equal to chi2 see chi, usually people write it up here. And then epsilon chi3 and keep going, right? It's a Taylor expansion of your electrical field. And notice here that I didn't write it down as e squared, okay, e to the third. It's because if you write it down in that way, then you can convert your vector back into a number. Okay, that's not what we want. Okay, so the way that you can actually maintain this term as a vector term, okay, is that to use tensor product. Okay, the reason, well, the way that the tensor product work is quite mathematically how it works. We'll just briefly explain here, because later, okay, we will just assume that all the polarization is aligned, and then you can drop the polarization. Okay, all the direction of the electrical field, they align. Okay, and then you can drop the vector here. Okay, this is what we will do in this class. And if you want to look down into here, we kind of have to get into what is a crystal and then what's crystal structure. So the vector, okay, how it work, the tensor, okay, how it work is that so here, instead of writing down as square that it returns to a number, you write it down as this, okay, E and E, okay, and then what this tensor can do, now when you multiply this coefficient in the front with it, okay, what it really do is that you can consider like this, okay, A, B multiply with C, okay, and then C first multiply with A, give you a number, and then you get a B remaining, okay, that's the vector. Right, so the tensor you can write down as, for example, a tensor can be like A, B, C, D, keep going. Okay, you just write in a row of vector, and then they do not do the inner product with each other. Okay, and every time you want to reduce the order of a tensor, right? For example, here you have tensor. Okay, the order is 4, okay. Order 1 means it's a vector. Order 2 is you just add another vector, okay. If you want to reduce the order, you just multiply with a vector, right? And then this time x will multiply with A and then give you a number, okay. So if you have a term that has 4e on the right-hand side, and then you want it to return as a vector, then what you can do is you can have an order 3 tensor multiply with an order 4 tensor, right? Then x times with A give you a number, y times with B give you a number, z times with C give you a number, and then you are left with one vector, one additional vector, okay? So here the way that we can apply that thought, okay, into writing down the Taylor expansion of nonlinear polarization is that your electrical field, okay, you write it down as a tensor, E, right? And then chi is again a tensor, okay? And then you can kind of know, okay, what's the order now, right? So you want to maintain when this chi multiplied with EE, okay, the net result here will give you a vector. Okay, so you can see that, okay, this is again the same. This multiplied together, this gives you a vector. Okay, so you can see chi3 has one order more than chi2 in terms of a tensor, right? Because it has one more E on this side to multiply to get back to a vector. Okay, and can keep going. And what it really represents, well, you might wonder, okay, this is what you argue in terms of mathematics, right? You want to align vector with vector. You don't want vector equal to number. What it really means in physics, right? Does it have some meaning here? Is that actually yes. What it really means is that different frequency, different polarization component, okay, they can interact with each other, right? So think about this. If you write down E squared, okay, what that means is that EX, if you write down as dot product, EX, EY, EZ, dot EX, EY, EZ, that gives you EX squared plus EY squared plus EZ squared. Right? So X interacts with X, Y interact with Y, Z interact with Z. Okay? But that's not really what happened in the material. In material, EX can interact with EY. EY can interact with EZ. And this is exactly how you ensure that happen, by writing down as vector. Okay? And then in this class, we'll not go into this. Okay, we'll not go into this. And if you're interested, you can you look at any, well, you can look at the textbook and it actually explains it. And then the notation for vector is actually, well, for tensor is actually different in different areas. So, but the underlying idea is always the same. Okay. Any questions? Okay. And that is actually it for today. And then we don't have class on Wednesday. I think it's reading day. And then I can double check the calendar, but I think it's reading day. And then next class, we'll actually look at this equation, okay? And then without doing serious calculation, just to kind of predict, okay, phenomenally, what would happen or what you can create, okay, with this equation with all these nonlinear terms, okay? And that's it for today. Thank you, guys.